Hi everyone. So in this video, we're going to continue to talk about integration by parts. So we're going to look mostly at some examples that are a little bit different from the ones that we saw in the previous video. But before we do that, I just want to remind you of what the integration by parts formula is, and we'll do just one example that is kind of a more standard example, similar to the ones from the last video. So the integration by parts formula is something that primarily is used to find the antiderivative of a product of two functions. However, we'll see in this video that there are definitely some other situations in which you can use integration by parts. So basically, if you're taking an integral and you have two functions, so one of them you're going to call u, and the second one you're going to call dv, then the antiderivative of u times dv is going to be the same thing as taking u times v. So that's the antiderivative of whichever function you chose as your dv. And then from that, you subtract the integral of v times du. So du being the derivative of the function u. So basically, it's a way to take a product that is too difficult to calculate, and you break it into these two pieces, and it does require that you then evaluate another integral, but typically that second integral will be easier to calculate. So I want to do an example just to kind of remind you how like a standard example for integration by parts works. So let's say that we wanted to evaluate the integral of x times e to the 3x. dx. So how do we go about choosing what we want to make our u and what we want to make our dv? Well, the idea is that, there's basically kind of two parts to it. One is that whichever thing you're picking for dv, you have to find the antiderivative of that. So you want to make sure that it's something that you actually know how to find the antiderivative of. But I think even the more important thing is that whatever you're choosing as u, you're taking the derivative of that. And so the derivative of u is going to show up here, right? And so in order to make your new integral an easier integral, one that you can actually evaluate, you want to pick a u that becomes simpler, ideally, when you take its derivative. So in this case, the choice that we would want to make is to set u equal to x, and dv is going to be equal to e to the 3x dx. So u is going to be equal to x, dv is going to be equal to e to the 3x dx. So why does this work? Well, now when we take the derivative, we get du is equal to 1 dx. So that's definitely simpler than just x. And then to find v, we have to do a very simple u substitution. And this is one of the ones that I think is kind of a good one to be able to do in your head. So what is the antiderivative of e to the 3x? Well, you might guess that it's e to the 3x, but that's not quite right? If you were to take the derivative of e to the 3x, you would get 3 e to the 3x, right? And so how do you counteract that? Because we don't want, we're looking for the antiderivative of just e to the 3x. How do we counteract this 3? Well, we counteract it with a 1/3. It's kind of like how the power rule works, right? With the power rule, you're always putting this kind of coefficient out front to counteract what's going on with the exponents. It's kind of a similar idea. So you could do this as a substitution, but I think it's kind of just makes this more complicated. And another thing to keep in mind, and this will come up later, is that in the problem, if you're using both integration by parts and then also substitution, you probably want to use a different letter. So if to go from here to here, you decided to use substitution, you were like, okay, I want to figure out what's the antiderivative of e to the 3x, because that's really what you're doing on this step. You would probably want to use a different letter. So maybe you would say let w equal 3x. And then dw is equal to 3 dx, and you could go from there. So you totally could use substitution. I just like to point out that sometimes it's not really necessary, and I think it's good habit to get into to not have to write all those steps out every time. Okay, that was a lot of talking. Let's actually finish this off. So how do we actually evaluate this integral? Well, we do u times v, so that's going to be x times the antiderivative we found over here, which I'll write that as e to the 3x over 3. And then from that, we're going to subtract the integral of v du. And so what is v? V is what we just had here, e to the 3x over 3. But du is just 1 dx. And so that makes our life a little bit easier. So now we have x e to the 3x over 3. And we can pull out this over 3 part for the integral as well. So minus 1/3 times the integral of e to the 3x dx. And we already just figured out a moment ago what the antiderivative is, right, for e to the 3x. So we're going to have x e to the 3x over 3 minus 1/3. And so what's the antiderivative of e to the 3x? Well, we just figured it out. It was e to the 3x over 3. And then we're going to have a plus c at the end. So altogether, this gives us x e to the 3x over 3 minus e to the 3x over 9 plus c. And you could make a common denominator here. I don't think it would necessarily make things a lot more simple because you would still not really be able to combine the two numerators in any real way. So I would just probably leave it like this. But if you wanted to make a common denominator, that would be fine too. Okay, so that is just like a kind of classic example of integration by parts. Again, what makes it a classic example? Well, we have a clear product of two functions, and we're picking the function that becomes simpler as our u and picking the other one as our dv. But there are other kind of more quirky examples where it doesn't go exactly like that. So I want to show you a couple of those. So we're going to use integration by parts to figure out what the antiderivative is of ln of x dx. So we haven't yet learned this antiderivative. It came up on one of the online homeworks, and that was actually just an accident. But I put in a note of what the antiderivative is, but we never actually officially learned this. So you might look at this and think, well, you can't use integration by parts on that. It's just one function. But you actually can. You can choose to make one of the functions just be like 1, right? Like you can think of ln of x as being 1 times ln of x. And that might seem like it's not going to accomplish anything, but it actually will. Okay, so we have to choose something to be u and something to be dv. So remember, we're trying to figure out what the antiderivative is of ln of x. We don't know what it is yet. So it would not make sense to call ln of x dv, right? Because then we would have to find the antiderivative, and we don't know how to do that. So we're going to choose to call ln of x u. So we're going to set u equal to ln of x. And then that leaves us with dv being 1 times dx. Okay, so what does that make du? Well, du is going to be the derivative of ln of x, so that's 1 over x dx. And then here to find v, we have to take the antiderivative of 1. And so the antiderivative of 1 is just x. So let's see what that gives us when we put it together. So we end up with u times v, so that is ln of x times x, minus the integral of v du. So that's going to be x times 1 over x dx. So as you might notice, things are going to simplify inside this integral, right? So we're going to get, let me just rewrite this as x times ln of x minus, and then, well, we have x times 1 over x, that's just 1, right? So we're going to have the integral of 1 dx. And so what is the antiderivative of 1? It's just x. So we end up with x times ln of x minus x plus c. So that is the antiderivative of ln of x. And the nice thing is if you ever forget it, it's not too hard to come up with it again. You just have to remember this idea. You just have to remember the fact that you have to use integration by parts to find it. And then you're really forced into choosing u to be ln of x, right? There's really no other choice. And it works out. So I'm not going to go through just for the kind of I want to make this a shorter video because I know the last one was pretty long. But you could totally check this, take the derivative, and you should see that you end up with ln of x if you take the derivative of what we have here. Okay, so let's look at another example that's kind of along the same lines. So we're going to figure out what is the antiderivative of inverse tangent or arctangent of x. So remember, similar to the last one, we don't know what the antiderivative of inverse tangent is, right? So we're kind of forced to choose u to be inverse tangent, because if we chose dv to be inverse tangent, we would have to find the antiderivative, and we don't know what that is yet. And then that leaves us with dx being equal to or 1 times dx being our dv. Okay, so now the derivative of inverse tangent is 1 over 1 plus x squared. So that means that du is equal to 1 over 1 plus x squared dx. And then v is the antiderivative of dv, and so that is just x. Okay, so let's put these pieces together. So we get, for the first part, we have u times v, so that's going to be inverse tangent of x times x. And then from that, we're going to subtract the integral of v, so that's x, times du, which was 1 over 1 plus x squared dx. So let's clean this up a little bit. So we have x times inverse tangent of x minus, and so I'm going to rewrite this as x over 1 plus x squared dx. So one thing I just want to point out, and this is something similar to what happened with the ln example, we started off with an integral that had inverse tangent in it, which was something we just didn't really know how to work with. But because the derivative of inverse tangent is something that just kind of looks a lot more familiar, it looks like a building block of integrals that we do know how to find, we're left with an integral that kind of looks a lot more friendly. And similarly with ln of x, right? Because the derivative of ln of x was 1 over x, it gave us an integral that just kind of had building blocks that were easier to work with than ln of x. Ln of x doesn't really combine well with other things. Similarly, arctan of x doesn't combine well with other things. But x and 1 over 1 plus x squared, those kind of interact in a better way. So specifically, what do we want to do for evaluating this integral? Well, this is a substitution problem, right? Because if we set our denominator equal to, so let's call it w so that we don't mix it up with the u that we're already using. If we set w equal to the denominator, then the derivative of 1 plus x squared is 2x, which is pretty close to x. So let's do that. So we're going to let w equal 1 plus x squared. And so dw is going to equal 2x dx. And so that means that dw over 2x is going to equal dx. Whenever we do these substitutions with where you use w, I always just think of the show Arthur. I don't know if you all are too young for that, but that's what I always think of. Okay, so what are we going to do here? We're going to put in w instead of the denominator. So we end up with x over w. And then we have times dw over 2x. So we get rid of those. And then we have x times inverse tangent of x minus the integral of, so now we're left with, let's pull out actually that 1/2 to the front. And then we have the integral of 1 over w dw. And so now we have something we know how to take the antiderivative of, right? That's just going to be ln of absolute value of w. Sorry, my screen gets really stuck sometimes. So we have x times inverse tangent of x minus 1/2 times ln of absolute value of w plus c. But then there's one issue, which is that we want everything to be in terms of x, right? So we need to go back to our substitution and put it back in. So our substitution was 1 plus x squared. So we can go ahead and put that back in for w. So we end up with x times inverse tangent of x minus 1/2 times ln of absolute value of 1 plus x squared plus c. And that's our answer. So a little more complicated than the last one, but it's the same idea. And actually, you can use this approach for any inverse trig. So I'll put on the worksheet a different inverse trig function, and the same kind of approach should work. Okay, so next I want to do an example that is, we'll see. I won't spoil it. This one is pretty different in the way it plays out. Okay, so this one we're going to take the integral of e to the x times sine of x. So just looking at it, one thing that maybe would strike you as being different about this one. So if you think back to the previous video, typically we would have kind of one function that became more simple when you took the derivative, and then the other one, maybe it didn't. But there was definitely always one function that became simpler when you took its derivative, whether it was ln of x, which becomes 1 over x, or whether it's like x that becomes 1, something that becomes more simple. Neither of these two functions, e to the x and sine of x, become more simple when you take their derivative. So we'll see that this is not going to go really like the other ones did, but we still just have to choose something. And so it actually doesn't matter which one you choose as what. I'm going to choose, because this is what I did in my notes, I'm going to let u equal to sine of x. And I'm going to let dv equal e to the x dx. But if you look in your book, they actually do the opposite approach, and they get the same exact answer. So it doesn't matter which one you choose. Okay, so that's going to give us du is equal to cosine of x dx. And then v is going to equal e to the x. So let's see what we get when we put this all together. So we get u times v, so that's going to be sine of x times e to the x. Oops, let me be consistent with my colors here. Minus the derivative, or the antiderivative of, so now we do v times du. So that's e to the x times cosine of x dx. So this isn't really much better than what we started with, right? Because we basically have the exact same problem with e to the x times cosine of x that we did with the original function. I'm just going to rewrite this so that I can use colors again and it won't get too confusing. So what's going to happen is we're going to do integration by parts again, and we're going to kind of make similar choices for what we want our u and our dv to be, and we'll see that basically we're going to end up back at the same integral that we started with, and we're going to be able to make use of that fact. So I'm just going to use u and v again. I don't know, maybe it would be better to choose two different letters like w and t or something like that, but I'm just going to use u and v again. Just know that these are new meanings for u and dv. So let's let u equal cosine of x. So last time we let it equal sine of x, let's do cosine of x. And let's let dv equal e to the x dx. So that would give us now du is going to equal negative sine of x dx, and v is going to equal e to the x. So if we put all this in, we have e to the x times sine of x minus, and make sure you're using parentheses here. So now we have u times v, so that is e to the x times cosine of x minus the integral of, so now we want du times v, so that's going to be negative sine of x. Actually, let me write it in the other order. Let's say e to the x times negative sine of x dx. Okay, I'm going to just simplify this a little bit, and I'm going to do one thing, which is, so, all along I'm just writing equals, 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 but let's put in actually what our original integral was, right? Our original integral was e to the x times sine of x. So now what we have is we have the integral of e to the x times sine of x is equal to, sorry, dx, I forgot that, is equal to the following. It's equal to e to the x times sine of x minus e to the x times cosine of x. And then what happens here? Well, we have a negative, so I'm just going to kind of combine these things. So we have a negative, and then we have another negative. So together, those become positive, but then we are also subtracting. So this is going to actually become minus a new integral of e to the x times sine of x dx. Hopefully that makes sense, and I didn't have to write out the other step. So again, we have a negative sign here. Pull that out, this becomes plus. But then we're trying to get rid of these parentheses, right? So if we distribute this negative sign in again, it will become a negative. So notice that we have the exact same integral on both sides of this equation, right? The first one is the integral we're trying to find, but then because of the way that, e to the x just keeps being e to the x, whereas sine and cosine flip back and forth, we got the exact same integral. And so we're going to do something that's like a little unusual here. We're going to actually add the second integral that we got. We're going to add it to both sides. So we're basically going to move all of these integrals, or the two integrals that are the same, we're going to move them onto the same side of the equation. And so why are we allowed to do that? Well, we have an equation, right? We know that the antiderivative of e to the x times sine of x dx is equal to everything else. And so once you have an equation, you're always allowed to do the same thing to both sides of the equation. And so what we're going to do is we're going to add that second integral from the right side. We're now going to add it to the left side. Or, we're adding it to both sides, but we're essentially moving it to the left side. Okay, so why is this a useful thing to do? Well, how could we rewrite, now we have an integral plus another of the same integral. Well, anytime you're adding two of the same thing together, you can rewrite that as 2 times whatever it is, right? So in this case, it's 2 times e to the x sine of x dx. And so now let's think back to what it is that we were originally, like, what are we actually trying to do here? We're trying to find this, right? We're trying to figure out what this antiderivative is equal to. And so now we basically are there. We have 2 times this is equal to e to the x times sine of x minus e to the x times cosine of x. So if we just divide both sides by 2, that will allow us to isolate the part that we're actually looking for. So if we divide both sides by 2, we end up with the integral of e to the x times sine of x dx is equal to e to the x sine of x minus e to the x times cosine of x over 2. And so that's our answer. So definitely a very unusual approach here compared to like all of the other types of integration we've done. And so this only really comes up in special situations, and it's usually going to be in situations where you have some mix of e to the x with a trig function, because they have this property where e to the x just kind of keeps giving you the same derivative and antiderivative, whereas sine of x and cosine of x, they switch, they flip back and forth. And so that's really what allowed us to come back to that same integral, which then allowed us to combine the two integrals and solve. All right, I want to do one more example in this video. So this last example is going to be one where we have to combine a couple of different methods that we've learned in this class. So this example is going to be, now it's actually a definite integral. So we're doing the integral from the square root of pi over 2 to the square root of pi of theta squared, or sorry, theta cubed times cosine of theta squared d theta. And I know we haven't been using theta a whole lot as our input variable. I'm not so good about varying it, but it's the same as if it was x, right? It doesn't matter what variable we're using. So for this one, you could try to do an integration by parts, but it's not really going to work from the get-go. And the reason for that is that basically you're going to be stuck with this cosine of theta squared, and the theta squared makes this complicated. So what else, like what other kind of methods do we have to work with to get rid of something like an input that is complicated, right? That's really the issue here, is that the input is something tricky. So how do we get rid of something like that? Well, we use substitution. So let's use the letter W this time for our substitution again. So we have W is equal to theta squared. And then dW would be equal to 2 theta d theta. And so that means that d theta, or I'll write it this way, dW over 2 theta is equal to d theta. So let's put that substitution in. Oh, and we also have to change the bounds, right? So the bounds are going to go from, so right now we have square root of pi, but we're squaring it. So that's just going to be pi. And then the lower bound, we have the square root of pi over 2, and we're squaring that, so that will become pi over 2. Okay, so let's write down our new integral and then see how to tackle it. So we end up with integral from pi over 2 to pi of, so we have theta cubed times cosine of W. And then we're multiplying that with dW over 2 theta. So notice that only one of the thetas is actually going to cancel out, right? We're going to get rid of this theta, but we're going to have to turn this into theta squared. So let's rewrite that integral and we'll see how we can deal with that issue. So we have now the integral from pi over 2 to pi of theta squared times, and let's pull the 1/2 out too. So we have over 2, I'll just pull that to the front. So times cosine of W dW. So initially it might feel like we're stuck, right? Because we already like dealt with the usually this is the part that helps you get rid of stuff in your integral, and we didn't. But remember that we already did the substitution, W is equal to theta squared, and so this is just another W. So we're going to end up now with the integral, or 1/2 times the integral from pi over 2 to pi of W times cosine of W. So it's just important when you're doing substitution, don't think of substitution as just like a one-time event. Think of it as this key that tells you how to go back and forth between your variables. And so in this case, anytime there's a theta squared, that's the same as W. So we can just put it in there, if, at any point if it shows up. Okay, so now we have an integral where we want to use integration by parts, right? Because we have a product, and this is similar to the first example we did in the previous video, which was x times sine of x. So we want to let u equal w, and then cosine of w dw will be our dv. And so how do we know to make that choice? Again, it's because we know that when you take the derivative of w, it becomes a lot simpler. And so we'll have a simpler integral to work with. And so we'll have du is equal to 1 dw. And then v is the antiderivative of cosine, so that is going to be sine of w. Okay, so now we're left with 1/2 times, and so we have to be really careful with all we're going to have like some parentheses going on here, right? Because we have 1/2 times this whole thing, but this integral is about to break into 2 pieces. So we have first u times v, so that's w times sine of w. And then from that we're subtracting, and then we have to evaluate that, right, at pi and at pi over 2. And then from that, we're going to subtract the integral of, from again, pi over 2 to pi of du times v. So that's going to be sine of w times 1 dw. Okay, so let's see what this all boils down to. So we're going to have 1/2 times, so let's actually, you can do it either way. You can either kind of find the whole antiderivative and then just plug in, or you can plug in as you go. I kind of like to do it as I go, but it might actually be easier, honestly, to just find the whole antiderivative and then plug in the numbers at the end. It doesn't really matter. But let's just go ahead and do it now. So I'm going to actually go over here to give us a little more space. So we have 1/2 times, so if you plug in pi, you get pi times sine of pi. And then we have minus pi over 2 times sine of pi over 2. And then from that, we're going to subtract. So the antiderivative of sine of w is going to be equal to negative cosine of w. So we have negative cosine of w, and we're evaluating that at pi and at pi over 2. So again, just be really careful. Like there's just so many places that you could make a mistake with parentheses or signs. So you just really want to be careful of that. That's definitely the biggest place people are going to go wrong in this. Okay, so what is sine of pi? Well, if you go to an angle of pi, the y coordinate there is 0. And so this, sine of pi is just equal to 0. Sine of pi over 2 is equal to 1. So we're going to get a negative pi over 2. And then over here, we're going to have plus. So let's do plus, and then we're going to evaluate cosine at pi. And then cosine of pi over 2. And I believe that's it, right? Yeah. So then we have 1/2 times negative pi over 2. And then cosine of pi is the x coordinate now, so that's negative 1. And then cosine of pi over 2, that's equal to 0, right? Because that's the x coordinate on an angle of pi over 2. And so what are we left with? We're left with, so there's a few different ways we could write this. So maybe let's start by multiplying in that 1/2. So we'd get negative pi over 4 minus 1/2. And then if we wanted to make a common denominator, we could write this as negative pi minus 2 all over 4. And that's it. So one last thing I just want to mention here, and this is something we'll kind of come back to in like a few videos. So in this class, for the most part, you're kind of handed these nice integrals that just happen to work out with the methods we're learning, right? So you can expect that if you go to the homework and do the homework questions that go with this video, they're all going to be ones where you can use substitution, and they're going to kind of fit with these methods. But one thing that is kind of a good thing just to keep in mind in the back of your mind is that there are a lot of integrals out there that actually we're never even going to learn how to do in this class, that actually require methods that kind of go beyond the type of calculus that we do in this class. So I just want to show you quickly an example of one that looks pretty similar to ones we've done, but that just doesn't work. So let me just write that down here. I'll say integration by parts does not work for every product. So one example would be trying to find the antiderivative of cosine of x over x. So it looks like a simple enough integral, right? Not too much crazy going on here. And you could rewrite this as x to the negative 1 times cosine of x, right? So you could see that this really is a product of two functions. So what would you probably try here? Well, we could try it both ways, but honestly, it seems like it would probably make the most sense to let u equal x to the negative 1. So let's try that. So let's see what happens if we let u equal x to the negative 1. And then that would mean that we would need to have dv equal to cosine of x dx. And so that would mean that du would be equal to -1, or I'll say it this way, negative x to the -2 dx. And then v would be equal to sine of x. So if we try to put these pieces together, we would get u times v, so that's x to the -1 times sine of x, minus the integral of, so now we do v times du, so that's sine of x times negative, all right, this way, times negative x to the -2 dx. So why is this not helpful? Well, the whole reason we did integration by parts was because we started with x to the -1 times cosine of x, and now we just have basically x to the -2 times sine of x, and that's even more complicated than what we started with. And then if we try to do it again, what will happen is we'll end up with an x to the -3. And so we're basically not going to ever be able to get this second integral to be simple, but we're also not going to get it to repeat back to exactly what it was. So we're not going to be able to use that special method where you end up with two of the same integral. So basically, this just doesn't work, and we're actually never going to learn how to do this integral in this class. So I just wanted to point this out, and actually maybe let me just say one more thing. If you tried to pick the other ones, and I'm not going to go through that in this video because you'll see it doesn't go anywhere, but if you tried to let dv equal x to the -1, so that would be 1 over x, then you would end up with ln of x, right? And so then you would have ln of x times, let me think, I can't do it in my head, but you would have ln of x times, some trig function. And so basically, again, you would get something that is kind of just more complicated than what you initially had. So I just wanted to mention this because I think it's a good thing to kind of keep in mind as a big picture idea, is that, we're really limited in the types of integrals that we know how to do in this class. It might seem like there's a lot of different ones to learn and a lot of different methods, but really we're only looking at a tiny, tiny fraction of the integrals out there. And it's not too hard to just come up with a relatively simple looking integral that we don't have the tools to solve. That being said, I'm not going to put one like this on the homework or anything. So you can basically expect that on the homework, you'll see examples that fit with the methods we used. All right, so the next video, we're going to learn basically how to deal with different types of integrals involving trig functions. So things like sine squared of x or sine of x times cosine of x, things like that. So I'll see you all in the next video.